we have Melkamu and Zeleke speaking. He's going to tell us about order trees, skew diagrams, and q-Catalan.
All right, I'm student number 6 or 7, I don't remember the particular order. I'm going to talk about order trees, skew diagrams, and q-Catalan numbers. This is quite easy stuff, and why in the world I decided to stand in front of the world's experts and talk about order trees and stuff like this. Well, I'm my advisor's student, so I take my cue from him. So let me show you. As a matter of fact, I was a little bit scared when a good friend of mine, Aaron Robertson, started to talk about stone check, compactification, and so on. He reminded me of the sleepless nights we spent together preparing for our qualifying exam. But anyway, the motivation for this particular talk comes from my advisor. This thing works.
Good view.
What do you want to visualize?
What did you do, Aaron? Yeah.
Control L.
Control L?
No,
It's
it's a different issue.
a different issue.
Mathematics has been an experimental science for the first 100,000 years of its existence. For a long, long time, people noticed experimentally very deep facts. For example, that 2 plus 2 equals 1 plus 3. And we proved it empirically by taking specific sets, 2 bells and 2 bells, like the same thing as 1 bell and 3 bells, 2 dogs and 2 dogs, and so on. So for a long time, mathematics was a nice empirical science. In ancient Egypt, ancient Babylonia, you measured 90 degrees by having a 3 by 4 by 5 rectangle. And they knew that that's a good way to make 90 degrees. And there was no so-called proof. Then about 2,300 years ago came a fellow called Euclid. And Euclid ruined mathematics.
All right, so I take my motivation from him. So 2 plus 2 equals 1 plus 3 is deep mathematics, so whatever I'm going to talk about is all right according to him. So most of you know that order trees, the number of order trees on n edges is given by the ubiquitous Catalan number. Those of you who have not seen this before, if you have 3 edges, those are the 5 order trees. I just want you to pay attention to a simple observation of a friend of mine, Lou Shapiro. I don't see he's up here. He looked at only the leaves among these ordered trees, and those are the red vertices there. And he observed that the total number of end nodes, or the leaves among these ordered trees, is half the total number of vertices, and offered to buy me a beer if I can get some kind of bijective proof for this. Before I talk about the bijective proof, since we are here to order Zeilberger, I'm going to talk about a proof that will somehow tilt towards his work. So let me talk about that first. A proof with the help of a CAD. I'm not referring to the computer, I'm referring to his Maple program. If T of Z is this generating function, where TLN is the number of leaves among all ordered trees with n edges at level L. So I'm trying to count by level, and this is the generating function. And This particular generating function, sorry, I'll be talking about generating functions a lot. They satisfy this nice functional relation here. This is not 1, it's L. The font is not that good. And it's very easy to see where this functional relation comes from. Very quickly, you just take an order tree, just pick any leaf. For example, you pick that one, that particular leaf, and then there is a unique path from the root to that particular leaf. And now if you follow that and then you try to retrace these, each of my edges are counted by z, and then you can wrap around. The C of z is again, the well-known generating function for Catalan numbers. And then from that picture, it's quite easy to see this functional relation up here. And once you have that, you apply the standard machinery here, TLN, you just apply the Lagrange inversion formula, and you get these nice expression for TLN, and therefore the total number of leaves here is going to be that sum. Some of you might evaluate these in about a minute, but here I'll just, I like these pictures. So, for a sum like this, or in general something that looks like this, of course, he wants to know who you're going to ask. In this case, you just go to his standard thing. These kind of things, as you know, will be evaluated using Zeilberger's method. In this case, if you put the summand into his program, it gives you this kind of occurrence relation here. G is given by this rational function times our summand here, which we got directly from the CAD. And then after that, you end up finding the total number of leaves to be that, and you put the ratio, and you obtain Shapiro's observation by day. Of course, I wanted to get my beer, so I have to also think about the bijective proof here. Since the quantity of leaves and non-leaves must be equal in number, it's natural to us if there exists a mapping or an involution between ordered trees. If we manage to get a mapping of the set of ordered trees onto itself that maps a tree with V vertices, that's important, L of which are leaves, to one with V minus L leaves, then you'll be able to get his observation very easily. And for that, I'll just simply show you a picture here. You start with an ordered tree. The skew diagram title comes from taking for each of, for example, you take this particular leaf, and you trace your path back to the root, so it's of length 2, so you put these 2 dots vertically up. And you repeat that for all the leaves. And then after that, pay attention to this particular skew diagram, and now you try to trace each one of them from the top row to the bottom. For example, the top row has 2 dots in there. So what that means is I'm going to draw a tree with a path length 2 up here, ending here, and you repeat that. And whenever there is an intersection, that means they share a vertex and so on. So that means the mapping of this ordered tree is into that. Notice that there are 4 leaves here and 3 leaves up here, and the total number of vertices up here is 7 and so on.